Goal of this lecture. Today I will say some question based on identity theorem or uniqueness theorem which had come in different type of competitive exam. First question, f be analytic function in the complex number C, then f is constant if the zero set of f contain the sequence an equal to 1 over n, b an equal to minus 1 to the power n minus 1 times 1 over n, c an equal to 1 over 2n, d an equal to n when 4 does not divide n, and an equal to 1 over n when 4 divide n. Here the question, when f is constant, if zero set contain the sequence. Zero set means z of f, if this is contain the sequence an such that this sequence converges to the limit point, where limit point belongs to the domain, then we can tell the function is identically 0. Obviously, f must be analytic, the domain must be connected. This is first condition. We all of us know, in my previous video I had discussed this part briefly. Today just I will discuss some question which had come in different type of competitive exam, and this exam had come in CSIR NET Exam. Here ZF contain the sequence 1 over n, and 1 over n goes to 0. So we can tell f is identically equal to 0. So option 1 is a right option. Option 2, an equal to minus 1 to the power n minus 1 over n. Here also ZF contain those sequence an such that an goes to 0. So by uniqueness theorem we can tell f is identically equal to 0. Here an equal to 1 over 2n. Similarly this goes to 0. Fourth option, very interesting. Here an equal to n when 4 does not divide n, and an equal to 1 over n when 4 divide n. Notice some terms m and some terms 1 over n. Here ZF is contain such subsequence, consider a4n, which and a4n goes to 0. So by uniqueness theorem we can tell f is identically 0. Many students would be wrong here, since here two part, so one part goes to infinity and one part goes to 0. But this result is true by the idea of subsequence. Since there exists one subsequence which goes to 0, so we can tell by uniqueness theorem f is identically 0. That means A, B, C, D both option is a right option. Example which also had come in CSIR NET Exam. The question is D be a open disk in the complex number C, and HD is the collection of all holomorphic function on it, and consider the set S equal to F belongs to HD such that f of half equal to half, f of 1/4 equal to 1/4, up to f of 1/2n equal to 1/2n. So on. Consider this set S and T equal to f belongs to HD such that f of half equal to f of 1/3 equal to half, f of 1/4 equal to f of 1/5 equal to 1/4, f of 1/2n equal to f of 1/2n plus 1 equal to 1/2n, so on. Then which of the following is true? Both S and T are singleton set. Second, S is singleton set but T equal to 5. Third, T is singleton set but S equal to 5. Fourth, both S and T are empty. Which of the following are true? Notice here D is the appendix in complex plane and ASD is the collection of all holomorphic function. And consider the set S equal to f belongs to ASD such that f of half equal to half, f of 1/4 equal to 1/4 and f of 1/2n equal to 1/2n. This is S set. Since f belongs to ASD where ASD is the collection of all holomorphic function, then obviously f is analytic and obviously the domain is open connected set. Here the function is defined from f from D to complex plane, and since here the S set is f belongs to HD such that f of half equal to 1/2, f of 1/4 equal to 1/4, f of 1/2n equal to 1/2n. For this, consider let gz equal to z. This is the consideration. And given f of 1/2 equal to 1/2, 1/4 equal to 1/4, up to 1/2n equal to 1/2n. So, since f of 1/2n equal to 1/2n, notice f of 1/2n equal to g of 1/2n which is equal to 1/2n, and this is true on the set S where S is 1/2n where n belongs to natural number. Obviously this set S goes to 0 and 0 belongs to complex number. So here by identity theorem we can tell fz equal to gz, and this is true on the set S. Since fz equal to gz, this is true on the set S. Therefore, and since here S contain the sequence 1/2n where n belongs to natural number, but limit of this set S goes to complex plane. So by identity theorem we can extend fz equal to gz on whole complex plane. I hope my all viewers have understood. Since by identity theorem we can tell this type of S is unique, because this is also the name of this theorem also is uniqueness theorem. So this is true, S is singleton set. Now I will see how look like the T. Next set is denoted as T where f belongs to HD such that f of half equal to f of 1/3 equal to half and f of 1/2 equal to 1/2n plus 1 equal to 1/2n. Notice here also f belongs to HD, so obviously f is analytic, obviously. But since t belongs to HD such that f of half equal to f of 1/3 equal to half and f of 1 over 2 equal to 1 over 2n plus 1 equal to 1 over 2n. Notice here also f belongs to HD, so obviously f is analytic, obviously. But since f of 1 over 2n equal to f of 1 over 2n plus 1, which is equal to 1 over 2n, this is, for this, we can consider Zz equal to Z. If we consider Zz equal to Z, then f of 1 over 2n equal to g of 1 over 2n, which is equal to 1 over 2n on the set S such that n belongs to natural number 1 over 2n. And this 1 over 2n goes to 0. So by identity theorem we can tell fz equal to zz on the set S. And since the limit point belongs to the set C, so we can extend fz equal to zz on whole complex number. But here Gz equal to, I have considered Gz equal to Z. That means Fz equal to Z. If Fz equal to Z, then f of 1 over 2n plus 1 would be 1 over 2n plus 1. But here, in the question has given f of 1 over 2n plus 1 equal to 1 over 2n. That means by identity theorem we can tell this type of function cannot exist. So obviously this type of function which indicate as t equal to 5. So B is a right option. S is singleton but t equal to 5. This is right option. Okay. OL. Next example, which had come also CSIR NET Exam. Similar type example. Let f be holomorphic function on the unit digits modulus of z less than 1 in the complex plane. Then which of the following is or are true? Option 1, if for each positive integer n, we have f of 1 over n equal to 1 over n square. Then that imply fz equal to z square on the unit digits. Here similar type. Here consider zz equal to z square. Then f of 1 over n equal to g of 1 over n, which is equal to 1 over n square on the set n such that 1 over n, and 1 over n goes to 0. So by identity theorem we can tell fz equal to gz. And since I have considered zz equal to z square, that means we can extend it, and this is true on the set S, fz equal to zz on whole complex plane. So option A is a right option. Option B, if for each positive integer n, we have f of 1 minus 1 over n equal to 1 minus 1 over n square. Then that imply fz equal to z square on the unit digits. This is not true, because here notice, let's consider zz equal to z square. Then given f of 1 minus 1 over n equal to 1 minus 1 over n, then g of 1 minus 1 over n equal to f of 1 over 1 minus 1 over n equal to 1 minus 1 over n square on the set S, where S equal to n such that 1 minus 1 over n. Notice S goes to 1. Here 1 be the member of boundary of the domain. Because mod z equal to 1, this is 1 belongs to boundary of the domain. But identity theorem always apply when limit point belongs to inside of the domain. So, by identity theorem we cannot tell fz equal to zz on the set S. I hope my all viewers have understood. So, here we cannot apply identity theorem fz equal to z square for the limit point 1. Third, f cannot satisfy f of 1 over n equal to minus 1 to the power n over n for each positive integer n. Is it true? F of 1 over n equal to minus 1 to the power n over n, which is equal to 1 over n when n is even and minus 1 over n when n is odd. This is not true because this type of function not be continuous. Since not continuous, that means it cannot be differentiated. So not analytic. So option C is a right option. F cannot satisfy this f of 1 over n equal to minus 1 to the power n over n. This is right. And option D imply f cannot satisfy f of 1 over n equal to 1 over n plus 1, and for this is true for each positive integer. Is it true option? For this, here f of 1 over n equal to 1 over n plus 1 for each positive integer n. Here consider zz equal to z over 1 plus z. Why I have considered zz equal to z over 1 plus z? Because here given f of 1 over n equal to 1 over n plus 1. If divide by 1 over n both sides, then this value would be 1 plus 1 over n. And put 1 over n equal to z, then this value would be z over 1 plus z. That means zz equal to z over 1 plus z. Obviously, G is analytic on mod z less than 1 and G 1 over n equal to f of 1 over n, which is equal to 1 over n over 1 plus 1 over n. This value would be 1 over n plus 1. Then, and this is true on the set S, where S equal to the n such that 1 over n belongs to natural, where n belongs to natural number. By identity theorem we can tell fz equal to zz on the set S. Therefore, by identity theorem, since S means 1 over n where n belongs to natural number and 1 over n goes to 0 and 0 belongs to C, then we can tell by identity theorem fz equal to zz, and this is true on whole complex number. Therefore, fourth option is also wrong option, because fourth option indicate f cannot satisfy this condition. But here I have got by identity theorem always I will get this type of function. So option 4 also wrong option. That means A and C, this is be the right option. I hope my all viewers have understood this is okay. Oh, our next example is similar to before, just as a review. I had indicated one more example about identity theorem. The question is, let D be subset of complex number be open index on the set Z belongs to C such that modulus of Z less than 1 and OD be the space of all holomorphic function on the set D. Then consider the set A equal to F belongs to OD such that f of 1 over n equal to e to the power minus n when n is even number and 0 when n is odd. And this is true for n greater than equal to 2. And B equal to set containing the f belongs to OD such that f of 1 over n equal to n minus 2 over n minus 1 where n greater than equal to 2. Then which of the following statement are true? Option 1, both A, B are non-empty. Option 2, A is empty and B has exactly one element. Option 3, A has exactly one element and B is empty. And option 4, both A and B are empty. For this, since F belongs to OD, therefore we can, and OD is the space of all holomorphic function, therefore we can tell, obviously, the function f is analytic. And here f of 1 over n equal to e to the power minus n and f of and when n is odd, then this value is 0. Here f of 1 over n equal to 0 when n is odd and n greater than equal to 2. Consider z equal to 0. And for this is true for all Z belongs to D. Obviously, since Z equal to 0, that means Z is analytic, similar to before. Then, if we consider the sequence Zn equal to 1 over n, then Fzn equal to Zn, consider this set S. On the set S, and this set has a limit point 0 which is belongs to on the D. So we can tell Fz equal to Zz by identity theorem. Since the limit point belongs to on the D, so we can extend Fz on the set Zz for all Z belongs to D. And since Fz equal to Zz for all Z belongs to D, that means Fz equal to 0 for all Z belongs to D. But here given f of 1 over n, when n is even, then this value is e to the power minus n. This is not possible. That means this type of function cannot possible. So, obviously, A is empty. Now I will see the set B. B is set f belongs to OD such that f of 1 over n equal to n minus 2 over n minus 1. And this is true for n greater than equal to 2. Equal to f belongs to OD such that f of 1 over n equal to n minus 2 over n minus 1. And this is true for n greater than equal to 2. For this, consider one function, arbitrary function zz equal to 1 minus 2z over 1 minus z. How we have to find the gz? This I have seen in few minutes ago. Since f of 1 over n equal to n minus 2 over n minus 1, just divide this by 1 over n. Then this value would be 1 minus 2 over n over 1 minus 1 over n. Now consider 1 over n equal to z. Then this value would be 1 minus 2z over 1 minus z. So consider zz equal to this type I hope my all viewers have understood. Now we have to find this type of Z. Here obviously G is analytic. So G belongs to OD. And here FZN equal to GZN. This is true on the set D because f of 1 over n equal to n minus 2 over n minus 1, which is equal to g of 1 over n. Because just put the value, this value would be, after putting this value would be n minus 2 over n minus 1. That means f of 1 over n equal to g of 1 over n on the set S, where S equal to n such that 1 over n belongs to natural number. And obviously this is goes to 0 and 0 belongs to D. So by identicality theorem we can tell Fz equal to Gz on the set S. And since the limit point belongs to D, so we can extend it Fz equal to Gz on the set D. I hope my all viewers have understood this is. So by uniqueness theorem we can tell this type of function exists and this type of function would be unique. Now notice the option. Option 1 indicate both A and B are empty. This is wrong. Option 2 indicate A is empty but B has exactly one element. This is true. Option 3 indicate A has exactly one element and B is empty. This is also wrong. Option 4 indicate both A or B are empty. This is also wrong option. I hope my all viewers have understood. Okay? Well, I will stop here. In my next video, I will discuss Schwartz lemma and some more example about this topic. But at first, I will hardly recommend you please see today's video with pay attention. Because if you don't see my previous video with pay attention and today's video with pay attention, then you cannot understand my next video in better way. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.